In today's lecture, I want to talk about the properties of the ROC, and this lecture is going to be divided in two parts. In this lecture, I want to talk about the properties of the ROC, and this lecture is going to be divided into two parts. So this video is going to be about the first part of the lecture, where we will talk about the different properties of the ROC of the Z transform. And you will see lots of similarities between these properties and the properties of the ROC of the Laplace transform. And we will talk about the characteristics of the ROC of different types of signals, namely left-sided, right-sided, and double-sided signals. The first property, which we will start with, which is a property of the ROC of the Z transform, is that it must be a ring in the complex plane or in the Z plane that is centered about the origin. So the ring is centered about the origin and may look something like this. So this is the Z plane or the imaginary, the complex plane. This is the real part, this is the imaginary axis, and the Z transform has the following ROC. So it's a ring, so you have an inner circle and you have an outer circle. And what is this saying is that the Z transform is, in general, may look something like this. So it's the inside of a ring that looks like this. Now, there are kind of extreme cases or corner cases where the inner circle is the origin. So this case would look something like this. So again, so the inner circle is the origin. So here, and I just have an outer circle. So here I would have the inner, the ROC would be actually the interior of this circle. And if you remember, this is exactly corresponds to the ROC of a left-sided signal. The third case that we can have corresponds to the outer circle corresponding to infinity. So we have the inner circle here, and the outer circle goes to infinity, which means that the ROC is the exterior of the circle, the inner circle. And if you remember, this corresponds to a right-sided signal. So basically, and we will see these again probably. So this will correspond. This is right-sided. This is left-sided, and this is double-sided. So this is basically what the property is saying. And mainly, I will not prove it, but you can find the proof in the book. But mainly, what it's saying is that for any point Z in the complex plane, you know that Z you can represent it by the polar coordinate. So you have the angle here omega and you have r, and this is saying that the convergence only depends on the norm r, meaning that if you have convergence at a given point Z here, so if the Z transform converges at Z, it must converge at any other point with the same norm r but maybe different angle. So it must converge on the whole circle here of radius r. So that's what it is saying. And so again, the general proof, I would not do it, it's in the book, but you can check it against the kind of the canonical example that we've been working on, which is the exponential signal. So if you have xn equal to an un, here I'm choosing a left-sided signal, I'm sorry, a right-sided signal, then you know that by now that that x of z is going to be equal to z divided by z minus a, and for this, the way we get this by using the formula of the geometric series, and we know that we have to have z, the norm of z greater than a. So you can see that for this example, it's clear that the convergence only depends on the norm of z. So this property in some sense is saying it's not only for these types of signal, but for any type of signal, the convergence will only depend on the norm of z. And therefore, what you have to keep in mind out of all this is, or remember, is that it has to look like one of these three cases. Either the interior of two rings, or the interior of one circle, or the exterior of another circle. So this slide here summarizes the takeaway of property 1, and these are the three types of ROCs that I explained. You have the interior of a ring, which is the interior of two circles, or the interior of one circle, or the exterior of another circle. So all the ROCs will look something like this. The second property of the ROC is that it cannot contain any pole, and this is clear because at the value of the pole, the denominator is 0, which means that h of z goes to infinity, so it does not converge. So just to give you an example, if you take h of z equal to z divided by z minus 1/2, let's say, then you have a pole at z equal 1/2 here. So you have a pole here. If you plot the pole 0 plot, and you have a pole at 0, and you know for sure that the ROC cannot contain the pole. So the ROC cannot be this, for example. So this cannot happen. So this is wrong, because the ROC here, as it is drawn here, contains the pole 1/2, which we know is impossible. So because it violates property 2. So always the ROC does not contain any pole. And again, the reason for that is that at the pole, the value of h of z goes to infinity, it does not converges. So here, for example, limit when z go to 1/2 of h of z is equal to infinity. And that's why the ROC cannot contain any pole. The third property is concerning the case when x of n is of finite length. So this means it doesn't go to infinity. And in this case, the ROC is easy to find because it's in the entire plane, except for two possible points that must be excluded from the entire plane, which are z equal to 0, meaning the origin, or z equal to infinity. And I'll try to explain this using an example. So let's take an example with, let's take x of n. Let's take a very, very simple example. So let's take x of n here equal to, let's say 2 delta n minus 1. And this means that, so this is xn. So this is 0, so it has value 2 at n equal to 1 and 0 other places. And then you know that x of z here is going to be, by definition, 2z minus 1, right? Now, when is this z transform defined, or where does it converge? It converges everywhere except for the case when z is equal to 0, right? Because 2 times z minus 1 is 2 divided by z. So here the ROC is the whole plane minus 0, because you're dividing by z and z cannot be 0. Now if we take another example, x of n, let me use a different color here. So let's take y of n, let's suppose, is 3 delta n plus 2. And then in this case, so this is how x of n will look like. So at n equal negative 3, or I'm sorry, negative 2, it has a value 3, and it's 0 everywhere else. And this will give you y of z is equal to, if you just apply the formula, so this is going to be equal to 3 z square. And again, you can see that everywhere you have convergence, except when z goes to infinity, then y of z is not defined because it also goes to infinity. So ROC here is equal to the whole complex plane minus infinity. So again, the reason why, because the limit of y of z is equal to infinity when z goes to infinity. And here, in the first case, the reason is that this goes to infinity when z goes to 0. So when the signal is of finite length or has finite support, the only problematic cases are when the x of z goes to 0. And here I have an example of a double-sided signal here. There is actually a typo, so this should be capital X of z. So let's suppose we have the z transform of a signal that is 4z squared plus 2z plus 3 plus 3z minus 1 plus 2z minus z minus 2 plus 2 to the power z minus 3. So these values, really the actual values do not matter. But you can see that this is a double-sided signal here. And the ROC is going to be the whole, and it's finite length. So it's going to always converge for any value of z except the two problematic values. So we're going to have a problem for z equal to 0 for these powers, z to the power minus 1, and z minus 2, and z minus 3. So we have to exclude z equal to 0. And we're going to have problem at infinity because we have these values for z squared and z. And these are going to go to infinity when z goes to infinity. So we have to exclude also infinity. The fourth property says that if x of n is a right-sided signal, and this is an important condition here, and if the circle with radius r0 is in the ROC, so here, then everything outside this circle must also be in the ROC. So this is why all this is in the ROC also. But this is under the condition that the signal is right-sided. So the ROC could be something like this, starting here. So let's suppose the ROC is all these things here. And then if R0 is, if the circle with radius R0 is in the ROC, then everything outside this circle must also be in the ROC. And you can see that this makes sense given our example of the exponential. We know exponential signal. We know that if for that signal, if it's right-sided, then the ROC is the exterior of a circle. So you can think of this as generalizing this property. For left-sided signals, we have a similar property which says that if the circle z equal with radius r0 is in the ROC, then everything inside the circle must also be in the ROC. So here the ROC could be something like this. Let's suppose the ROC is something like this. And everything inside of it is the ROC. And I know that if R0, the circle with radius R0 is in the ROC, then also the interior of the circle must be in the ROC. And then you can compare this to the example you know on the exponential signal with that is left-sided. So all these properties, you can think of them as generalization of things you've seen before. And if the signal is two-sided and the circle with radius R0 is in the ROC, then the ROC is a ring that contains that circle. So now that we went through all these properties, there's a few exercises to do at home, which is to find the z transform, which means find the z transform, find the expression of it as a function of z, but also find the ROC of the following two signals, x of n and y of n. And you're going to see the properties and apply the properties that we've seen before. So this is for you to try it at home.